Okay, so here's the fuel components. We have the 200 hour, 175 degrees C.
Hydrated nickel.
Yeah, and that was at what pressure?
20 bar, 300 psi.
And you did that in a little furnace.
Did it in a furnace inside of a stainless steel thermocouple tube, thermal well.
And the base of that was AH50 nickel.
Hunter.
Hunter nickel.
Yes.
Then the second one, this is the cheapest component, although it's had quite a lot of work done to it, so it's got a lot of added value, potentially, hopefully.
Yeah.
The second one is our aluminium.
This was packed in argon in the glove bag too.
Okay. So the second one is aluminium 18 oxygen, and this came from a Russian company, and it cost, there's 360 milligrams in this because we divide it between members of the project, but the 1 gram of that cost, I think it was nearly £1,000 for the gram, but we've got 316 milligrams here.
Pounds or euros?
Dollars, actually, nearly $1,000.
Right.
And then this is Nanosphere Nanonickel, as recommended by Brian Ahern, and this I think was about something like 360 for 3 vials of 10 grams or something like that. And this is the most expensive component here. This is the Trace Sciences Nickel 62, 96.19%. And this was around about 1,000 for 17 milligrams. So I don't know if you can turn that up so you can see the speck in the bottom. Can we see the speck in the bottom?
Yeah.
Yeah, that itty bitty little amount of material in there cost about $1,000. Mixing my currencies up here. So this is the reactor, and this is the scale of the hole that we have to try and get this into, which is here. It's pretty small, as you can see. And you've got this
to feed into it.
Yeah. So having tried to make some pills, and both Alan and Skip have been working very hard to try and find a way to make some pills to go in there. We've gone back to the sort of approach that was used in the Padua cell in Italy, which is exactly this funnel.
Yeah.
And copper, is it bronze or brass? Or
It's just brass.
Brass.
Yellow brass.
Tube.
Yeah.
And then
and this has been ground down just slightly so it fits in a 1/8 inch ID tube.
So can go in there. And then you've got this scale here. It's just fairly economical scale.
It's a cheap scale. It's for weighing gold or something, and it reads in 10 milligram increments. So to get our small 57 milligrams, we're going to estimate it.
Mm-hmm.
We'll get close. We'll get 60 milligrams and then take a little tiny bit away or something like that.
And for those people that have asked why we're not going to a high temperature with this, this is a very narrow hole, and we want to be able to recover. There's several reasons. One, we want to be able to recover this material for 5.5, the nickel there, and the aluminium 18 oxygen. And also, Brillouin's 25th of January presentation showed higher excess heat at 300 degrees C and almost nothing, well, very low excess heat at 600 degrees C. So that's another reason. But also, we saw our neutrons at around 304 degrees C core last time. So that's kind of why we're doing it at this temperature. And then you've got this weighing paper here, and that's hopefully where we're going to put everything.
It's the real deal.
It's the proper scientific weighing paper.
And we should just point out that the null side has nothing in it except a high purity alumina filler rod that'll go right down from the null side all the way to the start of the active cell. And on the outside of the active cell will be another piece of this filler rod. So there's nothing in here except for these 4 chemicals and high purity alumina throughout the reactor.
And so I'll stop and pause this video, but we're going to be mixing into this pestle and mortar.
Yeah.
And then trying to load it in.
And
so
off we go.
See you in a sec. That's the recipe. 62 nickel, hopefully 57 milligrams, 200 AH50, 543 milligrams, nano, what is it? Nano what?
Nanosphere.
Quantum sphere. QSI nano nickel, this one here. And that's going in up to 200 milligrams, and then the AL2 1803, 200 milligrams for a load of 1 gram.
Right. Okay. And then 43 milligrams. I have just checked the calibration. Okay. Back off, please. Back off, please. Thank you. It's in the light. So that'll be just over 54. That's reading in grams. Oop, went a little bit over. $540 milligrams. More or less. Use a new piece of paper. And I'm going to reset this because there's a timer on these scales, and you only get 5 minutes or something. The last thing you want is the scale to turn off when you're halfway through weighing a component. Okay, so this is the next one. No, we're going to save this until after, right?
Well, we're going to save it until after the nano nickel is
Okay.
on, because we want to dump something heavy on
So
top.
you were right. And so we're looking here, nano nickel 200 milligrams.
Yeah. Now this stuff is the lightest, smallest particles of nickel we have.
All
So
right, so hold your breath, Bob.
yes.
And this is black. There's 100. See?
May I lift the paper and then put another piece of paper on and tear it, and then then place it back down? Is that how we should do it? I put it in
So what's just happened here? The weighing scales have just turned off, so it's a little frustrating. Now that's why you use weighing paper.
Whoa.
There we go. And I'm not going to touch that because it'll get up in the air. So we'll carefully hit that with a wet wipe after we're done with this. And this we need to wipe off. How much do we have here? 316.
Yeah, so you want 200.
Why aren't we seeing anything? Oh, there.
Because this is very, very light.
So you can see the hunter nickel is the whiter, the greyer, and you've got the quantum sphere, which is very black. That's the 10 nanometer nickel, which is gets everywhere. And then there's the AL2 1803 on top. So we're now moving up the expenses.
Okay, you gave that a good wipe?
I did, not wet, but I did wipe it.
Yeah, okay. Now we need from here 57 milligrams, so that's going to read 5, but not 6. That's the closest we can do.
So nobody sneeze. Another good reason to have a face mask.
One more grain, maybe? What do you think?
I say stop, but
Yeah. Just under 6. So we're right in the ballpark.
Cool. Great. We've got a few more grains left in there for putting into 5.5. So that little dusting there, that's the sprinkle in the mix. It's interesting, they're quite large grain sizes, aren't they, those nickel 62? Interesting.
we don't need this anymore, right?
Don't close it because we got nano
I know.
stuff there.
I want to take it away and clean it.
Yeah, take it away and clean it. Just the barest damp towel.
I got it.
Okay. So, now I'm going to grind this all up and mix it together. Get rid of this for now. Oh, that's trapped in there.
May I take those weighing papers away and dispose of them?
Wrap them up inside of a towel, I think. Thank you.
One of those is probably worth about $200.
Say bye-bye.
No.
Now, there's grains of the 62 nickel quite large.
Fortunately.
Mm-hmm.
Anything else disposable?
Mm-mm.
Get rid of. I'll put it in the autoclave.
Yeah, those grains are chunky and they're not going to break up.
This is also bad stuff, isn't it?
Mm-hmm. But leave that for now because we're going to be filling the cell. Oops. I don't think I want to grind it anymore because it just sticks to everything. The quantum sphere stuff
Mm-hmm.
is so fine that it gets in the pores even of a ceramic like this. Yeah, stuff is really stuck onto the mortar. Quite a lot of volume here because these powders are so light, and I think we may have a little left over. When we put this in, we may have to punch it in a little bit, and I think we'll put a cover over this so that it doesn't come out in the air.
Mm-hmm.
I don't know, these details aren't clear enough. This is just a seat of the pants, but
But what you're worried about is that the fuel, when you put the fuel in, it might drop down here, so you're blocking this end.
well, these are a very tight fit, but nanoscale particles go everywhere.
Mm-hmm.
I'm worried that when I put the filler piece in the active end, it's going to create an air piston that forces the nanoparticles down into this part of the cell. And so what I'm aiming to do is to block airflow at this end by, we'll just put a piece of tape over it. Futile gesture.
Not futile.
Well, it's a well thought out attempt at engineering this system, yes.
All right, we'll restrict the airflow.
Yeah. Okay, so now I'm going to lift this up, and we need to be very careful of the thermocouple wires. And very careful of this beauty. And we need our funnel. And a tapping tool. This seems to work very nicely. I think I'm going to stand up for this.
Now there is a risk that you're going to get some sort of liquefaction of the smaller particles at the top, but by putting it in layers, there should be a better chance of some homogeneity.
Yeah, that is correct.
Skip's retired to a minimum safe distance.
Standing by.
I'm glad my camera's got a zoom. So yes, I know what you're thinking. The nanosphere, quantum sphere rather, nanonickel's most likely to go all the way down to the end, and that is a risk, but it hasn't. That particular nickel hasn't been treated in hydrogen in any way. It will have obviously hydrogen in the cell, but the main aim of this experiment is to see if we are seeing any neutrons or thermal neutrons or 511 keV from the 18 fluorine decaying back to 18 oxygen. Of course, if you do see that signal, it means that there are protons that have come out probably in excess of 4 megaelectron volts, and there's many papers out there that you can read that go into the science behind creating 18 fluorine, because that's used in positron emission tomography. And it's incredibly well studied, and there's a very good sweet spot at around about 5.2 megaelectron volts for creating 18 fluorine from 18 oxygen. And Pientelli is claiming that he has observed and calculated 6.7 megaelectron volt protons, so certainly capable of creating them, the 18 fluorine from the 18 oxygen, if it exists. And so that's why we have so much instrumentation on this experiment. Of course, you've got to be prepared for absolutely nothing. that's the life. I have to commend Alan on his steady hand here.
Steady left hand, vibrating right hand.
Okay. I wouldn't know what to do without you correcting me.
Happier?
How's it looking in there?
Pretty close.
Wow. Unless it's all in the brass tube.
Wouldn't be room, would there?
Well, there is that. Perhaps we should have thrown just a chunk of standard aluminium 18 oxygen in the bottom to just gum up the works. We found it was incredibly effective in the pill presses that Alan and Skip have been making over the last 2 days.
Tempting.
Yeah, when you pack the pill, it's very abrasive, the two constituents together, and they just bound into whatever pill press was designed and made it difficult to get out, nearly impossible.
Tore it up.
Yeah.
Okay, Skip, could you come over and hold the tube? Come around the back here.
I'm moving the seat away, don't sit
Yeah.
down.
Let me just scrape the rest of this down. Yeah, hold it up here. Good. My watch is complaining that I haven't moved in a few minutes.
Does that really?
Mm-hmm. I think that's about all I'm going to get out with a spatula. So, okay.
Stepping away?
Yes.
Excuse me.
Okay.
Oh, here we go. This is going to do a puff. Do you not want to put your fingers over the top? Oh dear.
No, I think that's all. It's really full.
Yeah.
You need that rod shortened?
I'm not sure.
If you do, I'll move it up to storage.
I had a piece of piano wire set aside here. There we go.
There's a tip for people. Piano wire. Very useful. Very springy.
Mm-hmm. Well, it's full up to about there.
Okay.
I don't think that's going to be a problem, is
No,
it?
no, I don't think so. I just need to make the filler rod shorter.
Yeah, let me keep working it down. Maybe it's
I'm surprised we didn't think of making a pill press out of those 2 bits of ceramic.
you can't hit them with a hammer.
Yeah.
And once the pill is in
Yeah,
there,
fair
it'll
enough.
never come out again.
Yeah. This is, it binds, doesn't it? I'm thinking we should make a special sort of rock climbing compound from it, where you just throw it into the crack in the cliff face, along with your whatever they call them. I'm sure someone knows what they're called.
So this one is uh, 2 5/8, and we need to take 7/8 off of that, so that's 1 3/4, right? My math correct?
Sorry, I wasn't listening to your math.
This is 2 5/8 long. And what we've got is, now I could probably get some fuel out. Should I do that? And then we'll have a sample for analysis?
Have we not got that on the tray?
No.
In there.
Let me do that, although it's going to make a bit of a mess. This is the time to do it. More.
That can be part of the larger fuel load in 5.5.
Moved a little bit. I think this is the right approach. All right.
Just mark that with a Sharpie and
No, I don't want you handling this piece because it's got stuff on it.
so you don't make that fresh.
Yeah. So 2 1/8.
1/8 long.
So this is our fuel sample for 5.4. One loaded cell.
something over this end a little bit?
No, I don't think it's going to come out of there on its own unless there's airflow. But I have to remove all the residue of adhesive from this end.
Well done, guys.